Welcome to this fourth video in the Introduction to R series. In this video we will be going through user-written packages and functions, and we'll be going through a brief introduction into how you would go about to make your own functions. So, contrary to commercial software, R comes with a fairly limited number of functions for doing different types of analyses. So a reason for this is because R is essentially a sandbox that provides the tools and materials to construct elaborate tools for analysis. Some examples of tools that would not come with R is, for example, the functionality to do structural equation modeling, exploratory factor analysis, to calculate the skewness and kurtosis of variables, etc. So R provides the necessary materials to do these types of analyses, but they do not necessarily come pre-assembled. User-written packages have then assembled these materials into analytical tools that have been shared for everyone's benefit. User-built functionalities is part of what makes R so powerful. So commercial software developers are usually slow or reluctant to add functionalities to their platforms. The R user bunch is very productive and program functionalities for everyone to use free of charge. So this is voluntary and unpaid work by members of the R community, and this is usually why you can find state-of-the-art analytical tools in R. So when you use these tools, you should credit the authors of the package with citations. So this goes for base R as well. R is made and maintained by volunteers, so you can find the citations for packages that you are using the citation function. So you write citation and you supply the name of the function that you want to, or the package that you want to cite. So you can, for example, take moments. Run this, and in the console you will find a printout of all the information necessary to cite the package. Now, to get the citation for R, you can simply type citation and run without supplying anything, and you will get the citation necessary to cite R. So some packages provide functionalities such as doing specific types of analysis. Others are made to change the way you work with R altogether, the Tidyverse family of packages being one example of these. So Tidyverse offers a number of functions that are intended to replace the basic functionalities provided by R, primarily with respect to data management and plotting. You can, in a sense, draw a distinction in the R community between those that prefer to work in Tidyverse and those that prefer to work with base R. This video series does not go into the Tidyverse way of working with R, providing instead an introduction to base R functionalities, and the packages that will be introduced does not intend to change the way you work with R. It simply extends the way that you use R. Moving on to installing and loading user-built packages. So installing external packages can be done using the install packages function, which takes a character vector with the names of the packages you want to install as input. So if I, for example, want to install the package moments, I use these quotes here and type in moments, run the code, and you see that the package moments has been installed on my computer. Installing a package on your computer is not sufficient to use it, in order to use the package, you have to load it into your R session. Now, you load a package into your R session by using the library function, and it takes as its argument the name of the package that you want to load. So in this case, moments. However, this time you do not enclose the name of the package in quotes. So if I run this code, nothing really happens in the console, but now I have the functions provided by the moments package available at my disposal. So for example, if I am to write the skewness here, you see that I have the skewness function available as the autocomplete here. And you see in these brackets that it is provided by the moments package. So you do not have to install packages every time you open R. Once you've installed a package, it remains installed on your computer until you either uninstall it or R. However, every time you open up R and you want to use a package, you have to load it. So while you only have to install a package once, you have to load the package every time you restart R and want to use the package again. So once you have loaded a package, the functions that are provided by the package can now be used the same way that you would use built-in R functions. So let me just generate some random data here. If I want to calculate the skewness now of this data using the skewness function provided by the moments package, I simply provide the R data that I made the data that I call the data here, feed it to the skewness function that is provided by the moments package, and it calculates the skewness of the variable. So you can actually make your own functions in R using the function. So the making a function that calculates skewness is actually pretty straightforward. So this here is then one equation for calculating the skewness of a variable. So here the xi is the ith observation of x, and x bar is the mean of x. Sx is the standard deviation of x, and n is the sample size. So implementing this equation here in R is pretty straightforward. So if we want to apply this to our data vector that I just made, we can use the following set of commands to do this. We start off with 1 over the length of our data, which then represents the n of the equation, and we multiply this by the sum of the observations, our data, minus the mean of our data. Raise this to the power of 3, and then we divide this by the standard deviation of our data raised to the power of 3. And we get this value minus 20, minus 0.20, etc., which is pretty close to the skewness calculated by the skewness function of the moments package. However, there's a slight difference because the moments package uses a slightly different equation to calculate the skewness of a variable. Specifically, the skewness function of the moments package uses the biased estimator of the variance. So I can actually make a function out of this equation here, so that if I would want to calculate the skewness of a number of different variables in a dataset, for example, I wouldn't have to write out this equation here every time for each and every one of the variables. So making your own functions can make life easier for you by making tedious repeat operations less cumbersome to perform. So in order to make a function that calculates skewness, I can make a new object here, which will be the function. I call this skewness in caps so that I avoid a naming conflict with the skewness function from the moments package. And I assign to this object the function. So the function is how you make your own functions in R. So you write the name of the function, use the parentheses, and then you follow these parentheses up with these curly brackets here. And it's within these curly brackets that where you actually write the function. Within the parentheses of the function, you specify the arguments that the function is to take. So now if we take this formula here for skewness, I can put this inside of these curly brackets. So the variable in this formula is then the R data, which was the data that I supplied to it. Now I can call this something else, for example X, which is the common way of treating the main input data. X, and I replace all of these R data with X. And if I now place X inside of here, and I run this function, you see that in the global environment, the skewness object has appeared under functions. So now I can use this new function that I've made and apply this to, see, X equals R data, and we get the output in the console here, minus 0.20, etc., which is the same as I would get if I were to run the above code. So this here is the specialized for this exact object here. Well, by writing this function, I've generalized this equation so that I can apply this to whatever vector of values that I want to, without having to write out this entire equation each time. So now I can just supply a vector of values to the skewness function, and it will calculate the skewness of the values in a vector without you having to write out the entire equation every time. So if I were to make a new vector of values, say we call this my norm D for my normal data, and we just randomly generate some numbers from the normal distribution, let's say 100 values here. If I want to calculate the skewness of these data, I can just supply the R of my norm D vector, and it calculates the skewness for this new vector of values without me having to write out the entire equation. Now we can make this function a bit more elaborate to have it do more things. So I can consider the case, if this my norm d vector consisted of some missing values, we can take here the first value of this vector and make it missing. If I want to calculate the skewness of this variable using this skewness function that we made, it will run into issues. Because the way we've written this function, it doesn't provide information to R of how to handle missing values or additional information with respect to how to handle missing values. So we can make this function handle missing values by taking the x argument. So remember that we assign this function with internal object here with the object or the vector that we supply to the skewness function. So if we take x here and say that the x object is to consist of x for which x is not equal to NA, so we basically just remove missing values from the x object within this function. If you run this, update our skewness function, and try to run this now, then it works again. So we can make the function a bit more elaborate by allowing the user to make additional inputs to control what happens within the function. So one thing that you might want to control in this case is how the function is to treat missing values. So in this case, the function will always remove any missing values from the x object within the function. Now we could make it so that the user has to specify that this is how the skewness function is to handle missing values. And we can do this by adding an additional argument to this function. Now let's say na.rm is the argument for which the user is to specify this behavior of the function. So this is then the common convention within R for how you specify within functions that missing values are to be removed. And we set this default value to false, which make it so that, and we want to make sure that for this line of code here to be executed, the user has to specify it specifically. So we do this by having a conditional statement here. We add the if statement, and we set the scope of the if statement similarly as we did with this function or with these curly brackets here. We move this line of code inside of the if statement so that this line of code is executed only if some condition is satisfied. So the condition that is to be satisfied is that this na.rm object, the functional internal object na.rm, is to be equal to true. So we do this by saying na.rm is equal to true. So if we now run this code here, we have updated the skewness function. So if we want then to if we run this code again now, so now it's once again the skewness function returns NA unless we specify, or now we are able to specify how that the skewness function should remove missing values from the functional internal object x by specifying na.rm is equal to true. And now it calculates the skewness again as it did previously. However, now we made the function a bit more elaborate by allowing the user to specify that the missing values are to be removed from the input vector to calculate the skewness. So that should do it for this video. We've been going through how we install and load user-written packages, where packages are called libraries in R. That is, they are libraries of user-written functions. We have also gone through a brief introduction of how to make your own functions in R, which allow you to automate, basically repeat operations, so that you don't have to write out long lines of code every time you want to execute it. You can package this code and generalize it by making a function out of it, which allows you to easily apply certain operations on objects instead of like using a simple function. By applying a simple function to the data, to the input object, instead of having to write out the code in full every time.